Okay, I'm sure you have learned kinematics of particles in a certain restricted or constrained conditions in your A levels, particularly particles moving in rectilinear space. As I mentioned at the last class, the kinematics deal with the motion. That is, we are interested in kinematic analysis. We are interested in finding positions, velocities, accelerations of a particle at different times as it moves. And I'm sure all of you know this vector representation of the space, our frame of reference. And any point in this Euclidean space could be represented by considering unit vectors E1, E2, E3 in the directions of X, Y, and Z respectively. So E1, magnitude of E1 equals E2 equals E3 equals 1. They are unit vectors. And they are orthonormal. That means they are perpendicular to each other. Therefore, their scalar product is 0. Scalar product is the dot product. So dot product is of two vectors, for example, vector A and vector B. I'm sure you know those from A levels. The scalar product of two vectors A and B, we know that it is magnitude of A modulus of B. Sorry. Cos theta. Since they are perpendicular to each other, this theta is 90 degrees. Therefore, cos 90 is 0. Therefore, the two vectors, dot product or the scalar product, will be 0. So that is something I hope that you are quite familiar with. So this kind of representation called orthonormal basis for a vector. Orthonormal basis for a vector, that is E1, E2, E3 representation, and any point with reference to this representation can be represented by using vector R, and R will have components of E1, E2, E3, component of the vector in the direction of E1, E2, E3. So in this case, X1, X2, X3 respectively. So, so this X is a function of time when the particle is moving in the space. X changes with time. And this representation can be, or this vector can be represented as a matrix in the form of X1T, X2T, and X3T. So the time dependent parameters of X1, X2, X3 in the directions of E1, E2, E3. And this vector can also be represented like this. So in real three-dimensional kinematic analysis, of course, it is very much advantageous for us to represent these vectors in the form of a matrix and use the matrix manipulation techniques or matrix we call linear algebra techniques to simplify and find different quantities that we are looking for. But in this first year level, we are not going to go into the motion of particles in 3D space. We're going to consider only in two-dimensional space. Therefore, just representing using vector just like this, and do simple manipulations would be enough for us. And also, you need to know a lot more about linear algebra, that is matrix manipulation techniques mostly, in order to use this matrix representation of vectors effectively. Therefore, just for your information, I just introduced this at this level, but for mathematical analysis, I'm not going to use it at this level. So the coordinate of any vector in any directional vector, or the or in other words, the x x1, x2, x3 components of any vector in a general vector can be worked out by considering the scalar product of the vector with respect to the direction that you are interested. For example, if you have a general a vector just like this, just like this, and if you want to find the component in the y direction, that is E2 direction, then you can take vector r dot E2, then you will be able to get the component of that vector in the direction of interest. In this case, for example, I considered E2. So likewise, the representation of vectors will be easy in a way, so that we can find out different quantities using vector algebra. So moving forward, now the velocity, by definition, these are mostly things that you know, but we are going to look at the quantities that you know in a more generalized form, and then we are trying to move into the particles moving in complex curves in 3D space. So 2D space rather. So we are going to relook at the derivations and the mathematical formation of these quantities, velocities, accelerations, and so forth. And then we can apply those to complex situations easily. If you consider any curve, any path of a particle moving, we call the trajectory of the point. That word trajectory is used to define the path. So if you're driving from Peradeniya to Colombo, your trajectory is the A1 main road, for example. And if you consider the motion of a particle along this trajectory in a very short time, then let's say the next, after delta t time, it goes to this point, and the vector representation of this advancement is delta r. Accordingly, the new vector, new position, can be defined as r plus delta r. So delta t is the small time duration, and delta r is the position difference between two time intervals. Accordingly, we define the velocity as the change of position divided by the time, and that is dr over dt. So dr over dt gives you the velocity of that particular velocity of the particle at this particular point. And of course, in a well-known notations, we could say V equals R dot. If you know the component velocities in the x, y, and z directions, with reference to the reference frame, then again you could represent your velocity vector again using this the unit vectors and the components of these velocities. Component of these velocities and the unit vectors will give you the velocity vector. And in the usual notations, we can represent it like this. I'm sure you are familiar with these sigma signs and things like that, so I'm not going to spend time on those. And the modulus of this velocity vector gives you the speed, that is we call the norm of this vector. So the norm is calculated by taking the square root of v dot v, the dot product of the velocity on itself, and then we'll get that this relationship. So this is more or less the speed. The norm of this velocity vector, or the modulus of velocity vector, is the speed. Now, the velocity is defined as I showed you a while ago, the change of this position delta r in a very small time duration delta t, and when delta t goes to zero limit, dr over dt defines the velocity. So that means when dt goes to zero limit, this delta r becomes smaller and smaller and smaller, and it becomes tangential to this curve at this point when delta t goes to zero. So when delta t goes to zero, the velocity component, this delta r vector is more or less coincide with this point, and the direction is tangential to this particular function. So velocity vector v is always tangential to the trajectory at each point of concern. So that is something that you know, and always the velocity is tangential to that tangential to the trajectory or the path at a given point of interest. Now, this when it comes to working out practical problems, not only just representation of these quantities in terms of position and time, we are sometimes interested in define these quantities with respect to the trajectory parameters. Now, for example, if you want to find the speed of average speed in general of a car, in general sense, from Peradeniya to Kandy, for example, then you just use a stopwatch and calculate the time that you take to go to Kandy from Peradeniya. You know the distance in kilometers from Kandy to Peradeniya, maybe 8 kilometers, and then you calculate the time and divide it by divide the distance by time and find the average velocity. Likewise, sometimes it is important and easy for us to know the represent these quantities in terms of the path, that is the distance moved along the path, that is s. So as we just looked at, v equals dr over dt, and then if I slightly expand this relationship just to include s into our discussion, then I can simply manipulate it like this. We want to bring the trajectory into our discussion. So now we get dr over ds into ds over dt. ds over dt is the speed. Therefore, our velocity vector v becomes v into dr over ds. So this v is the magnitude of the velocity vector, that is the speed. So this vector v, we know that this is velocity direction is tangential at this particular point A in this case. Therefore, dr over ds has to be a unit vector along this tangential to this curve at point A. So this is a unit vector tangential to the trajectory at point A. So that can be represented just like this. I introduce another vector, unit vector, et, that is the tangential unit vector. So the vector representation of the velocity is v into et. So that is et is tangential to the trajectory. So the trajectory parameter is considered in this case. So so that is the velocity, and then if we move on to acceleration. So as you all know, the acceleration is the time derivative of the velocity. So we know that v is r dot, then acceleration is v dot, or in other words, r double dot. And then so v equals v into et, that is we just looked at this one. And then if you take the derivative of time derivative of this quantity, then you will be able to find an expression for acceleration. And I hope you know how to do the derivation of two products like this. So one is a scalar, one is a vector. So this one you will get dv over dt, et, and this one is v dt over dt. So v dv over dt is v dot, that is the velocity in the tangential direction, and then we get a velocity component and det over dt. So v dot et, v det over dt. This is the change of speed over time, that is along the path, that is the acceleration, tangential acceleration. And of course, this is rate of change of tangential direction, rate of change of tangential direction. Now, if you look at et and det, there are two vectors. We don't know exactly whether this is a unit vector or not. We'll see what the magnitude of this one in a short time. And if you look at, for example, the directions of et and det, one straightforward thing that you can do is you can get the dot product or the scalar product of et, and if you take the scalar product of et and et and et, it is 1 because they are unit vectors. And if you get the derivative, then you get this one, det over dt et, and then the same thing comes here again, and this side becomes 0. Therefore, this if you look at this quantity, det over dt dot et is 0. Det over dt dot et is 0. That means they are perpendicular to each other. So definitely, when you take the derivative, they become perpendicular to each other. So so et and det over dt are two perpendicular vectors. So then, if we have defined this et as the tangential vector, therefore this is in the perpendicular direction to that tangential vector. Therefore, you could say it is a radial direction in the case of a circular path. So if it is a path is a circle, then et is in this direction, and perpendicular direction should go through the center, and that is let's say en. So this is the direction of det over dt. Just try to understand the magnitude of this. We worked out the direction of this, which is perpendicular to this one. And if we look at the magnitude of this, again, I will do a small manipulation. And I will dt over dt, and I will include ds in the middle. ds parameter I'll take into the discussion. So this is speed, and this direction is perpendicular to et. That is what we just found. Therefore, this vector is v into magnitude of et over ds, magnitude of det over ds, and the direction is en. En is defined as a perpendicular direction or a unit vector perpendicular to et. So that is det over dt. And the acceleration, of course, we earlier found that acceleration is this one. So this is the tangential rate of change of tangential direction, det over dt, and we were just looking at this one, and we just found it over here, and you can plug this in here. That is, you will get acceleration equals v dot et plus v squared. So there's v here, and there's another v here. So v squared det over ds into en, that is the normal direction. So this is the tangential direction, that is the normal direction. So so they are unit vectors perpendicular to each other, tangential to the trajectory and normal to the trajectory. Now, if you consider the special case, there is the familiar case when the trajectory is a circle of radius r. So if the trajectory is a circle of radius r, then we will be able to see what this dEt over ds is, whether it is a unit vector or anything else. We can look at the trajectory and two coordinates x1, x2, and we use the same basis vector to define our reference frame, that is E1 and E2 in the direction of x1 and x2 respectively. And the angle is theta. So this is r sin theta, this is r cos theta. Therefore, in terms of theta, we can say r equals x1 is r cos theta and x2 is r sin theta. And we know that this if the trajectory of this one or the distance moved from x-axis up to this point along the trajectory is s, then s equals r theta. Therefore, we can get rid of theta and represent this one in terms of s and r, because theta equals s divided by r. Theta equals s divided by r. So r cos theta is r cos s over r E1 plus r sin s over r E2 will define the position vector with respect to the trajectory. And then if you get the first derivative to find the dr over ds is this one, and this is the unit vector because you get the magnitude sine squared theta plus cos squared theta is 1. Therefore, this is the unit vector, obviously. And this one is perpendicular to r. If you take the product between this one and this one, then what you get is cos and sine term minus here. The same cosine times plus here, they cancel each other. Therefore, the dot product is 0. So it will definitely perpendicular to r. So r over ds is a tangential vector to the trajectory, and which is a unit vector. Therefore, that is our ET. That is ET. And then, of course, if you take the first derivative of ET, because we are interested in finding dEt over ds, and this is what you get when you get the first derivative, dEt over ds. And when you get the first derivative, of course, this vector will be perpendicular to this vector. Therefore, this will be normal to this one. So if you get the dot product between this and this, you will find it. The answer is 0. So this is a unit vector perpendicular to the ET, that is the tangential vector, and dEt over ds equals minus 1 upon r, and the direction of normal direction of ET as we defined is En. Therefore, the magnitude of dEt over ds is 1 upon r. So it is not a unit vector, at least for a circle. This is not a unit vector. Again, this is this discussion we do considering a circular trajectory circle, and this is correct only if the trajectory is a circle. So this dEt over ds is 1 upon r. Magnitude is 1 upon r, and that is called the curvature of the trajectory. R is the radius of curvature, and 1 upon r is called the curvature of the trajectory. And the direction is, if you define direction radially inwards, then we will get acceleration is v dot et plus v squared over r En. So this is something that you are very much familiar with from your A levels. So you, I think, considered motion in circular trajectories, and you calculated the accelerations using this equation. And of course, the significance of this equation is what is more important for us. That is, this is the acceleration in the tangential direction at a given point, and this is the acceleration in radial direction, and it has to be defined radially inwards. The direction has to be radially inwards, otherwise this becomes minus if it is radially outwards, so it is radially inwards. And then this whole part of this acceleration, that is the radial acceleration, is associated with the quantity dEt over dt. The previous, if I go to the previous slide, so that quantity is associated with dEt over dt, that is rate of change of tangential direction. So this acceleration component influences on the rate of change of tangential direction. Now this we talk about the radius of curvature here, and the radius of curvature, radius of a circle. If the curve is a circle, of course we can work out the radius of the circle. Usually the radius is given, or if the equation is given, we can find the radius, something like that. But if the curve is a complex curve, now sometimes you will understand when you do some tutorial problems. Now, if a particle goes along a complex curve, sometimes for analytical purposes, we can divide this circle into, the path into segments, small segments, a collection of segments, and we can treat each segment is circular. Even though the curve is complex, if you can't define the curve, now then you can divide the curve into small segments, and then we can consider each and every segment as a circle. So in that case, this will have a radius ρ1 and center O1, whereas this circle, this part will have center OI and radius ρi, and a part like this part will have a center somewhere up here, OJ and ρj. Likewise, we can define a curve. We can divide the curve into small segments, and each and every segment can be treated as a circle. So it's not the unique circle, but different circles at different radii get different centers. So that is some kind of an assumption that we do in most engineering analysis, and of course with these digital computers, these kind of assumptions we can effectively use nowadays with the power improvement or the increase of the power of digital computers, because we can divide these into very tiny small segments, and we can work out the motion between very small tiny distance, and then with the power of the computers we can integrate across and find out the final outcome. And of course, these kind of things sometimes we call circular interpolations. So we do in trajectory planning of robots, for example, whenever you want to go from one place to another place and avoid some obstacles and things like that, then sometimes we divide the trajectory into small segments, and then consider the motion between each segment either as a circle or either as a straight line, or in other words, some machining operations like computer numerical control machines, CNC machines. The path is defined sometimes using linear interpolations. That means two segments we consider as a straight line, or we could use circular interpolation techniques, where you consider two paths as circular paths. So that is something additional, but sometimes we'll have to do this depending upon the situation. We have to divide complex curves into small segments, and then we could consider, or we could treat each and every segment as separate segments. So whatever the case, there is a relationship, mathematical relationship, to find the radius of curvature of any differentiable curve. So if the curve is differentiable, then if d squared dy over dx exists, and d squared y over dx squared is not zero, then we can represent the radius of curvature, if you know the equation of the curve, just like this. So if you consider circular curves across small circular curves, then your equation for that particular instant is a circle. So if you know the equation of that circle, then you can find these quantities and get the radius of curvature. So these can be mathematically proven, but I'm not going to go into the mathematics of this, which is beyond the scope of our discussion here. But I have included how would you get this equation or the relationship for radius of curvature R by using trigonometry and calculus. So if you are interested, you can go through the things that I have just written down here. So they are simple things. Hope you will be able to understand clearly without a trouble.